Okay, so today we're going to talk about a couple of classical theorems that we can prove in using differential topology, at least in the smooth world. So these theorems are, the first one has a more general continuous version, but we will prove the smooth one. So it's the Borsuk-Ulam theorem. And I'm going to state and just prove the smooth version, but it has a continuous version as well. So, Borsuk-Ulam. So let f be a function from an n-dimensional sphere to Rn, smooth. Then there exists a point in Sn such that f of x equals f of minus x. So there are two opposite points that are mapped to the same element of Rn. Okay? So that's the statement of the theorem. And I mean, why is that interesting? I mean, there are some meteorological applications of it. I don't know if you've heard about that, but for example, if you look at the Earth, given any circle on the Earth, you can always find 2 points that are opposite to each other that have the same temperature. So this would be the application for n equals 1. And if you want to apply this for n equals 2, then you can maybe take a function, not just the temperature, but the temperature and the pressure, for example. And you can find 2 opposite points on the Earth that at a given point have the same pressure and temperature. Okay, so for n equals 1, you just fix one thing, so say temperature. For n equals 2, you want temperature and pressure. Okay, so that's a nice little application of the theorem. Okay, so any questions about it, about the statement? It's very simple. Okay, so let's prove it. So for the proof, we'll just use winding numbers, but everything in mod. We only really need z mod 2. Okay, so let's suppose not. Suppose not. So suppose that there doesn't exist an x like that. So we can define a function which is f of x minus f of minus x. And this function is going to be an odd function that never vanishes. I mean, I guess you can always define this odd function, but if you suppose that the statement is not true, then g never vanishes. Okay? So now this gives rise to a function g tilde that goes from Sn to Rn plus 1, and that misses the 0. And the function d tilde is just g of x 0. Okay, but because g never vanishes, then this g tilde never vanishes. Okay? So the claim that I'm going to prove in a little bit is that any g tilde of this form, so if g tilde is an odd function that doesn't hit 0, then the winding number of d tilde with respect to 0 is 1 mod 2. Okay, so this winding number is odd. Okay, so we're going to prove the claim in a little bit, but if we assume the claim, what can we do? Well, we know that, what is the winding number? The winding number is the same as the degree of g tilde over the norm of g tilde. And then now, we know that the point, that the line, I mean, the way that I define this function, if I look at the x, the last coordinate, this coordinate here, the line in this coordinate, so I can take, I don't know, 0, 0, 1 times r. This line doesn't intersect the image of Sn. So if you take, for example, 0, I mean, if you take the point...
You mean the intersection is 0, right?
No, the intersection is empty.
But any point of the image is... Oh, you're right. I'm sorry.
Yeah. Okay?
Yeah, I'm sorry. Yes.
No, that's okay. So this means that if I take the unit normal vector, you know, say this guy here, this does not belong to the image of g tilde over the norm of g tilde. Okay, so this g tilde over the norm of g tilde, remember, this is a function from Sn to Sn. Maybe I should put 2 dots. Okay, so what I'm doing is I found an element that's not in the image of this function. Sorry, I'm using image in this guy. It's always a little hard to write in this. So it cannot be in the image of d tilde over the norm of g tilde, because otherwise there would be an intersection here. Okay, so, you know, because it's not in the image, by definition it's transverse. This is a regular value. So this guy is a regular value of g tilde over the norm of g tilde, and hence the degree of this guy, I can use this vector to compute the degree, and this has to be 0. Okay, so this cannot be 1 mod 2. Okay, so this is the contradiction. Okay, so we need to prove the claim. So is it clear now, before I prove the claim, is it clear why the claim is enough? Okay. So we're going to prove the claim by induction. So first, the case n equals 1. So if n equals 1, let me just call, let me just drop the tilde, and I'm going to just say g is a function from S1 to R2 minus 0. which is odd. Okay? And I want to compute the winding number of G with respect to 0. And that's the same thing as the degree of G divided by the norm of G. So let me call this H, G divided by the norm of G. So H is going to be a function from S1 to S1. And it's easy to see that H is still odd. So H of minus X is minus H of X. Okay, and I'm thinking here, as S1 contained in R2 when I say minus X. Okay, the point is that when I have a function from S1 to S1, I can actually look at the universal cover of S1, which is R, and this gives rise, this has a lift. Any function from S1 to S1 has a lift to R, to a function from R to R. And this lift is given by, I don't know, I can write this function phi from R to R such that phi of X or T, and now I'm going to think about the elements in R as T plus 2 pi is going to be phi of T plus 2 pi times some integer, K, where K is an integer. Okay, so this is a kind of a simple observation, but you can deduce this either from the theory of universal covers, or you can think about this kind of explicitly if you've never seen fundamental group and universal cover. But anyway, I guess it's not very hard to believe that. The point is that this has to be a periodic function, and that this K is constant. It only depends on the map. And in fact, maybe this is a nice exercise. You can prove that K is the degree of the map that's induced by phi. So this doesn't require the function to be odd. This little observation. So every function from S1, every continuous function from S1 to S1 has a lift like this. And if the function is smooth, then you can assume that you can choose phi to be smooth. And the class, when you look at the class generated by phi down as a map from S1 to S1, this K is exactly the degree. Okay, it's not hard to see that up to a sign, they're going to be the same. But they're actually equal even with orientations. Okay. So now, since we actually assumed that H was also odd, we can say more than this. We can actually say that phi of T plus pi is going to be phi of T plus pi times K. And K is actually odd because H is odd. So by this exercise, K is the same K that appears here and that appears here, because this K is unique. So K is the degree of H, and it has to be odd. Okay, so that's the proof of the case n equals 1. Okay, any questions? No? Okay. So now suppose the claim holds for n minus 1. So it means that anytime you have a function from Sn minus 1 to Rn which misses 0 and it's odd, then the winding number of f with respect to 0 is odd, or is 1 mod 2. Oh, let me just say it's odd. Okay, so we're going to suppose that, and we're going to show that this claim is also true for n. So now let g be a function from Sn to Rn plus 1 minus 0, which is odd. Okay? And now we are going to look at the equator. So we want to reduce this to dimension n minus 1 somehow. So I'm going to find some sphere of dimension n minus 1 inside of Sn. And I guess the easiest way to do that is just look at the equator. So let this be the equator, i.e. Sn minus 1 is the intersection of Sn with, I guess, the boundary of Hn. It was a set of points such that the last coordinate is 0. Okay, I can draw a picture. I mean, I think everybody knows what I mean. But the equator also makes sense in higher dimension. No. Okay. And now I'm going to call H G restricted to Sn minus 1. So this is now a function that goes from Sn minus 1 to Rn plus 1 minus 0. So I can now, I'm going to do the usual thing, which is to just divide by the norm to get a map from a sphere to a sphere. So now I look at G over the norm of G, which is a map from Sn to Sn, and H over the norm of H, which is a map from Sn minus 1 to Sn. And now I want to find a regular value of both functions. So by Start's theorem, you can always do that. So let A be a point in Sn, be a regular value of both G over norm of G and H over norm of H. Okay, so because G is odd, since G and H are odd, minus A is also a regular value of both. It's also a regular value of both. And this means, actually, because A and minus A are regular values of both, it implies, hence, if you look at the line that's generated by A, this line intersects G and H transversely. Actually, we usually say the function intersects the submanifold. I mean, so hence G intersects the line which is generated by A, and H intersects the line that's generated by A transversely. Okay, but look at H. If you look at the dimension of H, the dimension of the line is one-dimensional. So there's not enough dimensions for these guys to actually intersect transversely if they do intersect. So in particular, this condition here means that H and the image of H doesn't intersect L. So this condition here means that H of Sn plus 1 doesn't intersect L. Okay, so now you can kind of see what I'm going to do. I'm going to project onto the orthogonal complement of L. Okay, but before doing that, so the idea is now I want to project onto L perp And because the image of Sn minus 1 does not intersect L, when you project into L perpendicular, you're going to get a map from Sn minus 1 to an Rn that doesn't hit 0. Okay. But before that, let's just see the following thing. So I want to compute the winding number of G relative to 0. So that, by definition, is the degree of the map G over the norm of G. And the degree of the map is just basically the number of pre-images of a regular value. So I look at, I know I chose A to be a regular value also of G over norm of G. So I can look at the pre-image of this guy. And I'm just looking at the number now because everything is in Z mod 2. So I'm going to look at these in mod 2. So I'm just going to, I don't need to worry about signs. And now, because G is odd, this is just going to be 1/2 of the number of points of the pre-image of L by G. Okay, so, you know, if, yeah, this is kind of, yeah, it's kind of straightforward from the definition that, you know, if you are on the pre-image of L by G, then either the image of the point goes to a multiple of A, or it goes to minus a multiple of A, or it either goes to a positive multiple of A or it goes to a negative multiple of A. Okay, so you see this all makes sense because because of dimension. So L is one-dimensional, and G goes from Sn to Rn plus 1. So because it's transverse, G is transverse to L, then this has to be a bunch of points. So let me say this one more time. The pre-image, if you look at the pre-image of L by G, that's going to correspond to that's going to be a bunch of multiples of A. And all the positive multiples of A will correspond to pre-images of A by G over G norm of G. And all the negative multiples of A will correspond to the pre-image of minus A of the normalized function. But because G is an odd function, you have the same number of pre-images of A and pre-images of minus A. That's why you get this 1/2 here. Okay, is that clear? And then the smart observation is actually that now we can, if you restrict G to the positive hemisphere, or to one of the hemispheres, so let's say G plus is the restriction of G to Sn intersection H n plus 1. Yeah, oh, by the way, I think, yeah, this has to be an Hn plus 1. So otherwise, it doesn't make sense. Because Sn sits inside of Rn plus 1. This sits inside Rn plus 1. Okay. So, you know, this, if I look at this this part here, this is my northern hemisphere, for example, and I'm defining G plus to be the restriction of G to this. Since the line L does not intersect the image of G along this equator, and again the function is odd, the number of points where G intersects L is just twice the number of points where G plus intersects L. So that's the other clever observation, is that this is now equal to the number of points, the number of pre-images of G plus. Okay, and I mean this is an equality mod 2 because the degree, the number of points, you know, the degree is the number of points with signs. So everything here is mod 2. Okay, but that's really nice. Because, well, we have this, what happened? Okay, great. Mod 2. Okay, So now we can do what I had said before. We can project, let me call this D. Oh, and the great thing is that the boundary of D is just this equator. And you see why this is going to be useful. So now I just project from Rn+1 to the orthogonal complement of L. Okay, so this is the orthogonal projection. And no, basically, it's easy to see that if you project G plus, for example, and if you actually hit 0, so the pre-image of 0, that's the same as the pre-image of L, of G plus. G plus minus 1 of L. Okay. That's just because the elements on Rn+1 that are taken to 0 are just everything that's on L. And nothing that's not on the line can get mapped to 0. Okay, so now we're almost there. Because we, because this projection composed of G plus, if you restrict it to the boundary of D, that's just the projection restricted to G, restricted to this equator. And that's a map from Sn minus 1 to L perp, which is, basically it's isomorphic to Rn, but it doesn't hit 0. We had seen it doesn't hit 0. So it has a winding number. And this winding number, by a proposition from last time, is equal to the number of points, the number of zeros of this function when you extend it to D. So this is equal to the number of zeros here. Okay, so this is, by this equality here, this is the number of pre-images of times that G plus hits L, the number of the times of that the image of G plus intersects L, and by this previous argument, this is just the winding number of G0 mod 2. And by the induction hypothesis, this is 1 mod 2. Okay, so that's the end of the proof. Okay, so we proved the claim, and therefore we proved the theorem. Any questions? Please ask. It's kind of a long proof. I can go back to if you don't remember something.
Could you go back again on the beginning when you were proving the first step of induction?
Yes.
So could you repeat why k must be odd?
Yeah, k is odd because the function h is odd. So I guess, maybe you should see it that since h is odd, then we can find a phi that has this form. And that's because, when you switch the sign of x, which is, what you can think about that as adding pi, then you have to have the same thing but with a different sign. So you can think about it as, just having the same thing plus a multiple of pi. Does that make sense? I mean, what I'm saying actually is that knowing the function is odd, you can actually even forget this part here and just go directly and say this equation has to be satisfied. Was that Pietro who was asking?
Yes.
Okay. Do you understand or not?
Kind of. Not really. I'm sorry.
No, that's okay. So how do you get this lift for any function of S1 to S1, or even this particular one? I guess you can think about it like this. You take. Let me see if I can explain this. Because I don't know if you've seen covering spaces before. Have you?
Yes.
You have. Okay. So anyway, so if you have a function from S1 to S1, the first thing you can do is you can sort of say there's a projection map from R to S1, and then it takes this is the function from S1. So this is just the map that takes, I don't know, X to, you can think of R S1 as R over 2 pi z, and this is R over 2 pi z. So your pi, this composition, will take a number t in R, and will take you to f of, I don't know, the class of t, something like that. And then now the idea is, well, I want to kind of find a lift from here to here. Okay, and this is always possible by the theory of covering spaces. And you can, for example, assume that you can see where 0 is taken. So where is f of 0? Well, 0 is going to be taken to some element of S1, and you can just choose that the lift to be some element between 0 and 2 pi. So you can choose this f so that f of 0 is some x0, some t0, which is some element inside of x 2 pi, like this. And the point, the theory of covering spaces will tell you that there is a unique way to extend this function to a function from R to R, which is a lift of f.
Yes.
And and then now what happens is, now that equation is kind of almost like a tautology from here, because sort of f of 2 pi is going to have to be t0 plus k times 2 pi, right? Because they have to be in the same class. When you project down here, they have to be in the same class. And this is the k that I said before. Is that clear?
Yes, but I mean, what is that? Why?
Why?
Yeah.
Because f of 2 pi, when you project it, has to be equal to the projection of f of 0. Because 2 pi and 0 are in the same equivalence class.
But this implies the k is odd?
No. Sorry, this is in general.
Okay, yeah, no, yeah.
Yeah.
I don't know why you can write this way.
Okay, so this is in general. But if you know that k is odd, then actually you can do more. You can do this for pi. So then f of pi has to be t0. Well, when you project f of pi, the projection of f of pi, oops, pi is too many things. Let's call this projection p. So when you project f of pi, this gives you, f of the class of pi, and this is f of minus the class of 0, which is minus f of the class of 0, which is minus p of f of 0. So the projection of f of pi has to be minus the projection of f of 0, which means that f of pi and f of 0 in the circle, when you look it up in R, they have to differ by an odd multiple of pi. So this implies that f of pi has to be f of 0 plus an odd multiple of pi. Otherwise, when you project to S1, you wouldn't have one is minus the other.
Okay, yes, you're right. Yeah, it makes sense.
Okay.
Okay. Yeah, I wasn't paying much attention that it was only pi, not 2 pi. Yeah.
Yeah, exactly. That's the point. Yeah. It's pi. Yeah. But now, the point is that once you have this equation, then you can apply it twice, for pi and then for 2 pi, and then you actually get this equation. So you have to, this k has to be the same k as this.
Okay, yeah, it makes sense. Totally.
Yeah, but you conclude that it's odd when you look at this equation.
Thank you.
You're welcome. Yeah, here you're just kind of using the fact that the circle is closed. After 2 pi, you'll get back to the same point. Okay, but apart, this is the case n equals 1 in the induction. So, yeah, and to see that case, the degree. If you just want this z mod 2, if you don't actually care about the orientation, this exercise is very easy. It's just to see that you have k pre-images inside the circle. Okay, so that should be straightforward. If the period, if as you go around once, you add a 2 pi k here, then you have to have k images. But of course, I'm claiming that even with the orientation, it's still true, so it's a little bit more subtle. Okay. Maybe it's not completely obvious, but it's it's still a nice exercise. Okay, but is the proof of the induction step clear? If nobody says anything, I will assume that you understood.
Vinicius.
Wait.
I got a question.
Yeah.
What can we do to get the same theorem in the category of continuous math? It's hard to.
You just need different tools, because the transversality tools don't work very well in the world of continuous things. Sometimes you can approximate it by. But I don't know if you can do this theorem using approximations. You can prove this theorem using homology theory, like using algebraic topology. Yeah.
Mm-hmm. Yeah. Thank you.
You're welcome. Yeah, a more direct way to do this is, but I think you would need algebraic topology, is if you're here, I suppose not, you can define this G, and then you can actually, if this odd function never vanishes, then you have an odd function G over norm of G that goes from Sn to Sn minus 1, and it's odd. So you can actually take that to be an odd function, to be a function from Rpn to Rpn minus 1. And then you can look at a little bit of homology theory of this guy here and apply it to the projective spaces to show a map like this cannot exist. Okay, so that's the continuous proof. So he uses the homology of projective spaces. That's why it's a little tricky. I guess this one is also tricky. You could learn algebraic topology without learning differential topology. So then maybe if you do that, then transversality is hard and homology is easy. So it's just about what you know and what you don't know. I would say they're equally hard, or they don't. The one is not particularly harder than the other. It's just the tools are different. And I've already advertised this. I'm teaching algebraic topology next semester, most likely.
I will be there.
Oh, good. Who was that?
Rafael.
Great. So I'll probably prove the same theorem for continuous functions using different tools.
Okay.
In a few months. Okay. So that's the end of the proof, but I want to know if there are questions about the second step, the induction step. I mean, I do find this argument pretty clever. It's from Gilliam and Pollack. Okay. All right, so now we're going to talk about another theorem, which I think is very, very pretty theorem, very well known. It's the Poincaré-Hopf theorem. And in some ways, it gives you a lot of nice, you can start visualizing a lot of things. You can see, you can basically, it's the first instance of real topological invariants that are defined from a differentiable standpoint. So now I'm going to talk about the Poincaré-Hopf theorem. So let X be an oriented manifold without boundary. And let V be a vector field. Okay? So if I pick a zero of the vector field, an isolated, so let's fix an isolated zero of V. So what does it mean to be an isolated zero? It just means that there exists an open set such that the only zero of X in this open set is P. So such that Vx is zero if and only if for X. The eraser is kind of small. Such that for X in U, Vx is zero if and only if X is equal to P. So I mean, of course, not all vector fields have isolated zeros. You can just take the zero vector field, and it's kind of too bad. It's a really bad in a sense, or really good in another sense, vector field. But let's start with vector fields that have isolated zeros. And for an isolated zero, we can define the index of zeros of P. So if P is an isolated zero, what can we do? So first of all, we can shrinking U, if necessary, we can assume that U is the domain of a chart. Okay, and then using this chart, we can see the vector field as a map from U to Rn. So this induces, or using this chart, we can see V as a map, V bar, from U to Rn. Okay, so I just look at the linearization on the tangent bundle, and I throw away the coordinate U, and I just keep the tangent. Okay? And this V, this bar is not very pretty. Okay. And this V bar of P equal to 0. So now I can look at the winding number of V bar restricted to the boundary of some little ball, maybe to be honest, something like this. Phi inverse of some little ball of radius 0. So if P is an isolated 0, I take a ball, a little ball. Then along the boundary of this ball, I don't have a 0, so I can look at this winding number. Okay, and this winding number is by definition the index of V at P. Okay, so now I can state an exercise, which is show that this index is independent of the choice of chart. Okay, so now I can state the Poincaré-Hopf theorem, and then after I state it, I'm going to actually do some examples. But the Poincaré-Hopf theorem says in these conditions, so if all zeros of V are isolated, then the sum of the indices of all zeros is equal to the Euler characteristic of X. Well, let me write a better chi. Chi and X are too similar, so I have to be careful. Chi technically goes under a little bit. Okay, this is the Euler characteristic. What is the Euler characteristic? Well, I can define it, and I will define it in a way that makes sense for our class. But maybe if you don't know what it is and you don't want to see another definition, maybe one way of seeing this theorem is that this number here is independent of V. The sum of the indices is independent of V. And you can just like choose your favorite vector field and then use that one to compute this Euler characteristic. And any other vector field will always have the same sum of indices. So an obvious corollary of this theorem is that if the Euler characteristic is different from 0, this is just a topological invariant, then any vector field has zeros. Okay, because if you didn't have any 0, then the sum on the left would be an empty sum. Okay, so let's look at some examples.
So the assumption in V is not that V has zeros and all the zeros are isolated. The assumption is if V has any zero, then the zeros are isolated. Right?
Exactly, yeah. So for all zeros of V, they're isolated, which means that if this condition is trivially satisfied if V has no zeros.
Okay.
Yeah. So let's look at some examples. So let's this index is something local, so we can look at some local examples. So let's start in the case of subsets of R2, so two-dimensional, two manifolds. So you could, for example, have so you can have locally, like let's say your vector field looks like this. So this is what's called a source. So what's the index of this vector field at this 0? You can write a local model for this. V of x1, x2 is equal to x1, x2, something like that. So a local model, so now you just have to look at the winding number of V when you restrict to a circle like this. So when you look at V restricted to say a little circle of radius epsilon, this is basically the identity. If you divide by the norm, it's going to be the identity. or something homotopic to the identity for any source. Okay, and what is the degree of the identity? Just 1. So the index is going to be 1. Okay, so the next thing you could do is you could do a sink. So a sink you can think locally as a vector field that goes minus x1 minus x2. And here, you have to look, the index will be the degree of the map minus identity along S1. And what's the degree of minus identity along S1? It's either plus or it's minus 1, but can you tell me which one it is?
Minus 1.
Minus 1? Why? So all you have to do is you have to see basically if this map minus identity preserves or reverses the orientation of S1. So
Yeah, because there is the rotation.
what? You have to be a little careful, but what happens is that, and maybe, I can't remember what I said last time. I might have said something wrong. But the degree of minus identity is not always minus 1. It's minus 1 or 1 depending on the dimension. So the degree of minus identity is basically the determinant of minus identity in the right dimension. So I mean, for S1 you can see it explicitly. So if you take this vector like this, what is when you look at minus identity, what's the linearization of this guy? So this guy is going to go to this guy when you linearize it. So actually get the same orientation. So minus identity preserves the orientation of S1. So this degree.
Assuming that the theorem is right, the Euler characteristic of the plane is always the same, right?
What?
Assuming the theorem is right, the Euler characteristic of the plane is always the same.
Yeah, I'm not actually looking at the Euler characteristic. I'm not looking at I'm just computing the index near a 0.
No, yeah, I know, but you chose a particular. Assuming that we can.
Actually, I forgot to write an assumption. So this is for compact manifolds. So the plane is not. This is not true for the plane.
Okay.
Yeah, because now I'm about to tell you of a vector field with a different index, that just has 1, 0 as a different index. But that was a good question, but the theorem is not true for the plane.
Okay.
So yeah, so here's another vector field that you can look, and it's the saddle. So you can a local picture. I'm doing all these calculations locally, and yeah. So it's V1, V of x1, x2 is minus x1, and then x2. And then this, it's interesting. Now you can check that the sort of the index of this guy is going to be the degree of this map here, the complex conjugate or something like that. I'm going to call this R of reflection, and the degree of the reflection is minus 1. Okay, why? Well, if my reflection says like this, then if I take this vector, the linearization of the reflection is going to take this guy to this guy. Okay. So more generally, I should say, that if you have the identity from Rn to Rn, the degree of the identity restricted to Sn minus 1 is going to be minus 1 to the n. And if you take the reflection, which just changes one sign, x1 to xn is minus x1, x2, xn, the degree of the reflection is minus 1. Okay, this is actually a very simple calculation. You just take the bases and you just see what happens. But with minus identity. Okay. So that's gonna basically tell you that if you have if your vector field takes x1, xn, and it switches a certain number of signs of them, then the index is going to be either minus 1 or plus 1, depending on this numerology. Okay, but let's go back to the surfaces because it's kind of interesting. Now we want to look at closed surfaces. So for example, if you look at a sphere, and now we can look at some vector field that just kind of is the derivative of what's going down along the sphere. So if you can think about this as embedded in R3, and you look at the gradient of the height. So you have a vector field that goes like this. And then you see in this case, I have one source and I have one sink. So it's not very hard to compute the indices here. So the index here on top, if this is P and this is Q, the index on top is going to be 1, and the index at the bottom is also going to be 1. So the Poincare-Hopf theorem says that the Euler characteristic of this S2 is going to be 1 plus 1, which is 2. And it also says that if you take any other vector field on the sphere, it always has to have, the sum of the indices always has to be exactly equal to 2. Okay. So maybe one thing that's kind of interesting is, maybe I can write this as an exercise, is find a vector field on S2 with a unique 0. Okay, so if it has a unique 0, then the 0 had better have index equal to 2. So you basically have to look at some, I'm going to give you the hint. The hint is to look at the function that function z goes to z squared. So the vector field locally near its 0, it's like x squared. So what is that? x1 squared minus x2 squared, and then 2x1, x2. Something like that. So I think it goes like this. I think that's what it is. So something like that. You can double check the picture. But I think this is the picture for the vector field given by that. And you have to kind of prove that you can extend this to the sphere, S2. And compute the index of the 0 is exactly equal to 2. That's easy because the degree of this map, we already know the degree of this map is 2. Okay, but I think doing this exercise will give you, you start to play with topology really and see, how to build cool things. Okay, so now let's look at genus G surface. So we haven't classified surfaces yet, but you probably know that all closed orientable surfaces are like this. So it's a connected sum of a bunch of tori. Okay. And then I can do something similar. I can look at the gradient of the height function. So when you look at the gradient of the height function, that will have some zeros. The maximum and the minimum, of course, but then for each of these holes, you actually have two saddle points here. So, you know, you have this like this, and you have it like this, coming out like this. So anyway, I'm not going to draw everything, but the top is going to be a source. The bottom is going to be a sink. And then you have a bunch, you have actually two G saddles. Okay, so by the Poincaré-Hopf theorem, the Euler characteristic, I'm going to call this sigma G, a surface with G holes. This is going to be, so 1 plus 1 minus 2G. 1 plus 1 minus 2G. So 2 minus 2G. And if you want, you can do a very interesting exercise. It's harder than this one, but I think it's on a list, a problem set of when I taught the class last time, is find a vector field on this surface with exactly 1, 0, with exactly 1, 0. Okay, 4G different from 0. And for G equals 0, you can find a vector field on a torus with no 0. Okay, so this is a little bit harder because it's really harder to see the surface, but a hint is to look at, you can look at sigma G as a polygon, as a 4G gon with sides identified. I don't know if you've seen this before, but maybe I should say, you know, if you want to look at a torus, you already know that you have this dum, 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 dum. So A, B, and B. So if you want to construct a surface of higher genus, you can look at, so for example, sigma 2, you can look at an octagon, 1, 2, 3, 4, 5, 6, 7, 8, and then you do it like this: A1, B1, A1, B1, A2, B2, A2, B2. So that's how you get a surface of genus 2. So you have to think a little bit, but it's not very hard to see that when you fold it, when you glue A1 with A1, B1 with B1, A2 with A2, and B2 with B2, then you get exactly this guy. And you can do the same procedure for any genus. Okay, so it might be easier to draw the vector field over here. Okay, so that's a cool little topological exercise. Okay. All right, so let's go towards the proof of the theorem. Are there any questions, comments?
Think about the example of the sphere.
Yeah.
I take the constant vector field in R2, in R3,
Yeah.
like up, and perturb a little bit near here. It's not
The constant vector field in R3, it's not going to be tangent to S2.
Yeah, and then I project it to the tangent space.
Okay.
So the problem will be in P and Q, right? It will be 0.
Yes.
So I could change a little bit the the vector fields near here to not have 0.
No, you cannot remove the 0 through a projection, through a perturbation.
Why is that?
Well, one way of seeing this using the machinery that we have is if you take the 0 and you take a neighborhood of the 0 and you look at the winding number of the vector field on this boundary, which is actually how we define the index, that is invariant under perturbation. So if you perturb the vector field, I mean, there are several ways, but one of them is, yeah, if this number is different from 0, then this winding number, then when you extend it to the interior, it always has to have a 0.
I see.
You see? I mean, maybe you're imagining something, but what you're imagining, I don't think it's actually true. Like, if you take a constant, I don't know, going in a different direction, when you project it to the tangent space of the sphere, you're still going to find 2 zeros somewhere else. If you just perturb a little bit, then the 0 is going to be close by. But if you
Which
perturb
is
a lot,
strange, right? Yeah.
what? Yeah.
Yeah, I can see.
You see?
Thanks.
Okay. You're welcome. Other questions? Okay, so let's go towards the proof of this theorem. But before, let me make one more definition.
Sorry,
Yeah, go ahead.
just an idea. And if we sum to this vector field some vector field that's non-zero in one of those points,
Yeah.
then
you might have a 0 somewhere else completely far away.
Oh, so you get another 0, like.
You could get another 0 somewhere else, yeah.
Okay.
Yeah.
Você pode pegar duas cartas na esfera, que cobrir a esfera com duas cartas, e definir x quadrado em uma, constante igual a uma na outra, e colar com a parte da unidade?
Sim.
Funciona aí?
Você tem que tomar cuidado, porque a partição da unidade é um pouco perigosa aqui, né? Eu acho que a forma mais fácil de você fazer é olhar a esfera como sendo R2 com mais um ponto no infinito.
Certo.
Se você mostrar que isso aqui você consegue entender. Porque o problema, né, tem alguma coisa especial de Z2 que não vai funcionar para Z3 ou para Z4. So there is something special about the number 2 here. Because otherwise you would prove this in the other characteristic of S2 is any number. So the point is, if you look at another power of Z and you try to do the same thing, then you won't be able to, you actually have to have a 0 at infinity as well. So somehow you have to see the what's happening with Z2 is very important here.
Eu não sei, mas acho que meio você pode definir o campo como sendo, sei lá, um dx1, e aí definir ele como 0 no polo norte, e depois usar uma projeção estereográfica para mostrar que está bem definido na outra, né? Na do sul, no caso.
Definir como... essa é uma outra ideia interessante.
Só para você mostrar que é bem definido na outra, no caso, na projeção sul, né?
Aham.
Mas acho que esse vai, não sei.
Exatamente, essa é uma forma, talvez, dá para fazer isso explicitamente, eu acho. Mas eu acho que tão bonitinho, tão legal quanto é fazer o desenho na própria esfera. I mean, in a way, I think, you could, well, I'm already giving too many hints, but if you just want to draw a picture, you can kind of start by going like this, and then going on the other side like that. And then you see that this you can actually extend to something that goes like this through the South Pole. Topologically, this is, oops, I putting the arrow the wrong way. So topologically, this is what's going on. You have these circles that go all the way, and they kind of, you can take these circles to get bigger and bigger and bigger and kind of go through the sphere like that. So, yeah, you have to show that you can extend this vector field over the South Pole, and it's non-zero there. Okay, so I'll let you do this exercise at the level of precision that you'd like. Maybe some of you will do the whole calculation. Maybe for other ones, this picture is enough. But in particular, I'd like you to see that it doesn't work for Z3, or where it fails for Z3. It's actually kind of cool, because if you try to do it for Z3, then you would have a 0 up here of index 3. So you'd have to compensate it with a 0 of index -1 somewhere else. So if for Z3, if you want to play around with this, you actually can do you can put Z3 here in the neighborhood of this guy, and then you have to have a saddle here, and then you can fill in. With a non-zero vector field, apart from the North Pole and the South Pole. Okay, well, we can have fun with this. Now let's go towards the proof of Poincare-Hopf. Okay, so we talked about isolated zeros to be able to define the index, but isolated zeros are not good enough. They're actually not generic. What is really generic is a simple zero. So if I take a vector field and just a point such that VP is equal to 0, we say that P is simple if 0 is a regular value of the local representation. V bar. Okay, so if there is a chart where zeros are, when you look at the local representation, 0 is a regular value. It's kind of obvious that it's true for every chart. And then maybe an exercise is that if P is simple, then the index of P of V at P is either plus or minus 1. I'm kind of going to do this exercise in a way or another a little bit later, but maybe just for you to stare at this and think about whether you see this or not. But anyway, the more interesting exercise, which I like a lot, and I think you can kind of see what's happening, is if P is an isolated point, is an isolated 0 of V, then you can perturb V. Then there exists a V tilde, which is another vector field, which coincides with V outside a neighborhood U of P, such that all zeros of V tilde in U are simple, and the index of P is the sum of the indices of all the zeros v tilde, so vx is 0 for x in u. Let me draw a picture. If I have a 0 of a certain index, I don't know, let me draw my nice index 2, 0. Then it means that I can perturb, the exercise is saying I can perturb my v. So if I do a little perturbation, but just in a neighborhood, u, outside u, I keep v constant. And now this 1, 0 is going to transform itself into two zeros. So you can kind of see it from this picture here, that I can do it like that. Okay, so this is, well, you can do this in general. Maybe not diffeomorphic, homotopic. So this basically means that if you're trying to prove anything about vector fields, you could just assume that all zeros are simple. Okay, so now we can actually prove the theorem. So any questions about this exercise? So we may assume, without loss of generality, that all zeros of V are simple. Okay, again, it's basically by transversality. Okay, so now I can let ft from x to f to x to x be the flow of V. Okay, so it just means that df of ft is V at the point ft. Okay, so if t is a positive number and is small enough, sufficiently small, then the only fixed points of the flow they have to be zeros of V. Then the set of fixed points of f of t is the same as the set of zeros of V. I mean, it's clear that if you're a zero at V, then the flow doesn't move. So this inclusion is always true. But if you let your flow go on for a while, it's possible that you can start somewhere, and then you can, the flow can take you back. You could have like something like this, a closed loop. But this is kind of a simple exercise in ODEs that if you take the time to be small enough, then if you're not at a zero, then you have to move away from the original point. You cannot close up. There is a minimum time to close up. Okay. So I mean, this is not completely obvious, but it's some, if the manifold is compact, then for t small enough, then you cannot have a closed loop that's not a trivial path, fixed constant path. Okay. So now is the kind of smart, the little observation, which is that we can think of the fixed point, or the fixed point of Phi t, or the zeros of V, as an intersection. So now if you let delta be the diagonal, so this is xx in x times xx. So if you want, this is the zeroth jet. the image of the zeroth jet of the identity map. And you can also define the graph to be, I think you know what this is. It's just the zeroth jet of the function f, the image of that zeroth jet. Okay, so I guess I can write this down. This is x and ft of x. The smart observation is that the set of fixed points of a function is the intersection of the diagonal with the graph of the function, or there's a bijection. So there is a clear bijection from the set of fixed points to the intersection of the diagonal with the graph. Of phi t. Sorry, it's not phi, it's f. Although my f and my phi look alike. Okay, so my claim is that the diagonal intersects the graph transversely, and that the index of x, and that for every point in the intersection, and for every x a0 of v, the index of this guy is equal to the sign of xx, where this is the sign of the intersection point xx in the intersection of x of the diagonal with the graph. Okay, so this is the claim, and I'm going to prove that in a little bit. But let's see why the claim is enough to prove the theorem. So now, I have a bijection between the set of zeros and this intersection. So now, and I know that this the index is just the sum, it's just the sign. So it's either +1 or -1, depending on whether this intersection is plus or minus. So that implies that the sum of the indices for all the zeros is going to be the intersection number between the diagonal and the graph of ft. But now, if ft, t is a fixed t, right? So if I fix t, which is strictly positive, this is actually homotopic to f0. The flow just gives me the homotopy as I move t, and f0 is the identity. So this is going to be homotopic. This is going to be equal to the intersection between delta and the graph of the identity. The graph of the identity is delta itself. So this is the intersection of the diagonal with the diagonal. And if you think, if you can take this actually to be the definition of the Euler characteristic. This is the differential topology definition of the Euler characteristic. It's just the intersection of the diagonal with the diagonal. Okay, so that is the proof, the end of the proof of the theorem, assuming the claim. Okay, so that's the last thing we have to do is prove this claim. Any questions before that?
How hard it is to prove that the intersection of the diagonal with itself is equal to the usual definition of
it depends what you mean by the usual definition.
I mean, using Betsy numbers or something like that.
Well, I'm going to show you in a little bit. I'm actually going to show you using the Poincaré-Hopf theorem that this number, this Euler characteristic, is the sum. If you use triangulations, it's the number of cells, the alternating sum of the number of cells of each dimension. So maybe that's going to be that you'll be happy with that one. But anyway, let's finish the claim and the proof, and we can talk a little bit more about the other characteristic. So since the claim, any other questions? Okay, so since the claim, now let's prove the claim. So since the claim is local, we can assume, we can just look at everything locally. We can look in local coordinates, and we can think of V as just being a vector field in Rn. So we can think of V as being a map from a subset of Rn, an open subset of Rn to Rn, such that the preimage of 0 is 0, and 0 is a regular value. Sorry, I want to say the preimage of 0 is just the element 0. And 0 is a regular value. Okay, so now I kind of have to solve the first exercise that I gave you. So by the inverse function theorem, and now I can use this heavy inverse function theorem. I think if you look in Gilliam and Pollack, they do a proof that goes around this. I think they don't even perturb it to be simple. But if you actually assume that the zeros are all simple, then you can use the inverse function theorem, and then basically you have the identity except for orientation. So up to an oriented diffeomorphism, V is either the identity or it's the reflection. That's kind of, I mean, you can but using the inverse function theorem, you can always get the identity, but then it's not necessarily oriented. So if it has the wrong orientation, you have to compose it with the reflection, and then you have the right orientation. Okay. So now you just have to look at the index of V at the point 0. Now it's going to be either +1 if V is the identity, or -1 if V is a reflection. Okay, so let me call this number Q for now. So Q is a number that's either plus or -1. So what we have to show is that when you look at the intersection of the diagonal with the graph, that first it's going to be transverse, and second that the intersection number, the sign is the same as this Q. Okay? So, well, let's look at the flow. So what is the flow of V? So the flow of V is very simple. So V is either the identity or it's the reflection. So the flow is going to be either, it's going to be e to the qt times x1, and then e to the t times x2, etc. Okay, because my reflection is just the reflection of the first coordinate. So r of x1, xn. Let me remind you what the reflection is. I defined it a few minutes ago. So r of x1, xn is minus x1, xn. Okay, so the flow is going to be e to the qt, x1, then e to the tx2, e to the txn. Okay, so now I want to show, now we will look at, well, the tangent space to delta and the tangent space to the graph of ft at the point 0, 0. So you start by choosing an oriented basis of Rn. So fix an oriented basis of Rn. So, I mean, let's take, V1 through Vn. This is the fixed oriented basis of Rn. Okay? So then we get an induced oriented basis on the product. And how do you orient the product? You know, there's a natural orientation on the product, and whenever I don't say anything, I always consider the natural orientations. But the natural orientations on the product are basically, you know, first you pick the bases on the first coordinate, and then you pick the bases on the second coordinate. So, you know, that's the oriented basis is something like v1 times 0, vn times 0, and then 0 times v1, and then 0 times vn. That's the induced orientation on the product. Okay? And what is, given this oriented basis of Rn, what is the oriented basis of the diagonal? So the oriented basis of the diagonal is like v1 times v1, and then vn times vn. That's what you get. And similarly, you know, you get an oriented basis on the graph of every function by just applying the derivative to the vector. So in fact, an oriented basis of the graph, and now at 0, 0, so I have to look at basically v1 times the derivative of f of t in the direction at the point 0, 0. You know, you just take the natural vector in each direction. So this is just going to give me q times v1. No. Yeah, sorry, at 0, the t is not 0, so I have e to the qt, yeah, that's right, times v1, and then I have v2 times e to the t times v2, and so forth. vn times e to the t times vn. That's the oriented basis that I have. So now I would like to see if this basis and this basis together generate the whole tangent space of the product. So, you know, I would like to look at what is the span of this guy and this guy. So I just look at, you know, I can just concatenate the two bases, and I'm going to have a set of vectors. And I can write that in the chosen induced oriented basis of Rn times Rn. So I can write this string of the two bases above as a matrix in the oriented, in the natural base, in the canonical basis, if you want. Canonical basis of Rn times Rn. So basically you have to write each one of these in this basis here. So this will give me the following matrix. So identity, that's the first n columns. And then the next n columns is going to be identity, and then I have e to the qt, e to the t, e to the t. Okay. Okay, what's the determinant of A? Can someone see? How is your linear algebra? I claim that the determinant of A is e to the t minus 1 to the n minus 1 times e to the qt minus 1. Do you see that? Maybe there's an intermediate step, which is just, you can show that this matrix, you can find a determinant 1 matrix, which you can multiply this A by, and you get identity, and then you get this matrix that you had. Let's call this matrix B minus identity. So the determinant of A is going to be the determinant of B. Okay, so this step here is very similar to something I did before with when we were talking about, what was it, immersions. I think when proving with the immersion theorem, I did something, a trick kind of similar to this. It's a simple trick in linear algebra. But anyway, so now you can see that, you know, this guy here is always positive because my t is positive, and this guy here is either positive or negative. This has the same sign. The sign of this guy is equal to q. Okay, so we see two things. First, the determinant is always different from 0, which means that these two tangent spaces span the whole thing. So it means that the diagonal is transverse to the graph at 0, 0, because the determinant is always different from 0. And you also see that the sign, which is the sign of this determinant, which is telling you the sign of this intersection point is equal to q. And the sign is equal to q. And remember, q, it was by definition the index, or the sign of the index, which is the same as the index. Okay, so this is the proof of the Poincaré-Hopf theorem. And I want to finish just saying a little bit about the Euler characteristic. So the way that we defined it is kind of a little funny. Like, we use some somewhat obscure intersection theory fact to define the Euler characteristic. And then we say, well, look, you know, if with this obscure thing, then the sum of the indices of vector field is equal to that. But maybe you could think of it as, like, you know, the other way that I said, you know, the theorem just is telling you that the sum of the indices of zeros of vector fields is constant. So to compute this constant number, which I'm just claiming to be the Euler characteristic, you just have to choose a vector field. So for example, if you have a surface, a closed surface, you can triangulate it. And this fact itself is not trivial. But if you believe that you can triangulate S, that means you can write S as a union of triangles whose interiors don't intersect and whose boundaries, you know, just intersect along these edges. So I'm not going to define what a triangulation is, but I think you can imagine what it is. The definition takes too long. But anyway, so if you can triangulate a surface, then you have vertices, which I'm drawing in red. Then you have edges. And you have faces. And now what's really cool is that if you have a triangulation, then you can actually construct a vector field which has a 0 at the center of every face, or like in the interior of every face, in the interior of every edge, and at every vertex. So, you know, basically what you do is you take the interior of every face, or you take a fixed point, say the center, and you make that a source. And then you make the interior, this fixed point in the middle of every edge, a saddle point. So you always kind of flow down to a lower dimensional object. Sorry, my picture is a little bit messy, but I think you see what I mean. So this means that each face corresponds to a source, each edge corresponds to a saddle point, and each vertex corresponds, or each vertex is a sink. Okay, so when you have a triangulation, you have a vector field like this that maybe it's not completely obvious it's smooth, but it's at least smooth by parts. You can choose your vector field to be smooth, and if the triangulation is smooth in a certain sense, then you can actually smoothen the vector field. But there is some kind of condition about corners or edges where you glue the faces, where you glue the triangles. But not worrying about this, you see that by the Poincare-Hopf theorem, this Euler characteristic, whatever it is, some fixed topological number, is equal to the sum of the number of faces minus the number of edges plus the number of vertices. And this is probably, if you want, the classical definition of the Euler characteristic for surfaces. And in higher dimensions, you can do the same thing. Like if you have a manifold, a triangulated manifold, then it just means that you can split the manifold in simplices of higher dimensions. And a simplex, the boundary of a simplex is given by a bunch of simplices, and there is a stratum depending on which codimension you are. But you can do exactly the same thing. You can take the middle point, and there you can have the middle of the simplex, and there you can have you can put a source, which is defined in every dimension, and then the next codimension, the first facet, then you kind of have something of degree 1 less, and then the next thing you have something of degree 1 less, and all the way down to the vertex. So sort of the higher, here in the middle of this space in the three-dimensional picture, you have a source like this, and then if you're in the middle of a facet, then all the directions that are contained in the facet, you're going out, but then the direction coming from the other the codimension 1 thing, you're going in. And then you kind of just lose one direction of going in, or you gain one direction of going in until the point where you get to the vertex, which is going to be a sink. Okay? So you can see that the facets, as you go from 0 facets to 1 facet to 2 facets, you change the sign of the index. So that the Euler characteristic will be, the sum of -1 to the n times the number of n facets. Okay, well, we have to be careful with the sign, but it's basically that. And if you want, if you've seen Euler characteristic before, this is maybe the classical definition.
Can you triangulate every manifold?
That's a really subtle question. You can triangulate every smooth manifold. And the question of triangulating topological manifolds is much more subtle. I think the answer is actually no. But I think it's a very recent theorem by Manulisco for topological manifolds. But in general, it's a very hard problem to triangulate manifolds. But it's the classical way to do algebraic topologies through triangulation. That's how people used to do algebraic topology in the early 20s. In the early 20th century. And then they realized later they could use singular homology and do much clever things. But Poincare, I think, did everything with triangulation. Okay, so someone... Yeah, so someone's saying, James is saying, Hauptvermutung. Oh yeah, someone. Yeah, so Ciprian Manulisco proved that there exists compact topological manifolds of dimension 5 which are not homeomorphic to a simplicial complex. So I think there was already a 4-dimensional example that was not triangulated. 4-dimensional topological manifold that was not triangulated, has been known since the 60s or 70s, but I think Manulisco proved that in dimensions 5 and higher, you can still find topological manifolds that can't be triangulated. But anyway, this is it's very interesting question, but kind of outside the realm of this course. Okay, any other questions, comments?
Uma curiosidade, na verdade. Esse número que você definiu, o número de facetas, ele coincide com a dimensão da homologia no nível da dimensão?
Eu também estava perguntando isso, parece os números de Bethe.
Exatamente, coincide sobre R, né? É um pouquinho complicado, porque você pode ter homologia... a homologia pode ter partes cíclicas. Então, na verdade, não coincide porque você pode sempre aumentar a triangulação, né?
Entendi.
Mas assim, você consegue uma triangulação mínima. Essa questão até não é tão óbvia, mas assim, dá para você... Triangulação mínima eu acho que não, mas se você consegue uma decomposição celular mínima, eu não sei nem se dá para fazer isso sempre. Mas a questão é que o número, essa soma alternada é igual à soma alternada dos números de Bethe. Mas, em geral, o número de Bethe é a dimensão da homologia. Isso é menor ou igual que o número de faces daquela dimensão. Porque você tem a homologia simplicial, ela é gerada pelas faces, né? Então, o número de geradores é igual ao número de faces. Então, a dimensão da homologia é menor ou igual que o número de faces, mas não é necessariamente igual. Só vai ser igual se a diferencial for 0. Mas, bom, a gente pode falar sobre isso no próximo curso, no semestre que vem. Bom, então tá, pessoal. Passamos um pouquinho do tempo. Mas a gente continua, então, na terça-feira.
Vinicius.
Oi.
Just a question about the test. That's going to be the last class before the test, right?
Yes, that's right.
Okay. Thank you.
Yeah, the test is going to be Wednesday. Yeah, but the content, I mean, next time we'll talk about the Hop theorem and the Pontryagin Tom construction, and that's not going to be on the test. So the test is going to be up to today.
Ok, thank you.
Okay. Beleza, pessoal, então, bom fim de semana e até terça.
Tchau, professor. Obrigado.
Tchau.